extra elements for this comparison operation to enhance its properties. So we have seen that comparator can be single stage, comparator can be multiple stages configuration, comparator can be open loop, it can be feedback loop, comparator can be with regenerative latches also. So slowly we are looking at each and every possible implementation and trying to find out the expression for delay and the other properties. Okay. So in our quest for a good implementation of a comparator, we were discussing in the last class a two-stage open loop comparator, which is a simple op-amp, which is now working as or giving us a comparison operation. So simple two-stage op-amp that I have chosen is shown in the slide. As you can see, this we were discussing, and we assume that it has two-pole response. It has two dominant poles as given by the expressions. We write the transfer function in Laplace domain. Then from Laplace domain, we move back to the time domain by taking inverse Laplace, and we get an expression for our V out in the time domain in terms of V in that we are applying. So V in is usually, we assume that there is a step signal. That it is a step signal. Suddenly we apply a step difference between the two input terminals, and accordingly output will come to a particular logic state, maybe logic 1 or logic 0. Because we are assuming that my output will either go high or go low, because this is what I am interested in. I am not interested in between values. I just want to know whether my input is more than the reference or reference is more than the input. That's all. So we have got the expression for our V out in terms of two poles. As if we that my two poles are close by, then I can work with an explanation or approximation that P1 is equal to P2. Though it is not a very correct approximation, but we assume, because we just try to have an idea first of all. So we tried the simple case where we assume that P1, P2 are overlapping each other, and then we try to solve this expression for V out of T, which gives me the expression for V out in terms of P1 equal to P2. We define a ratio M is equal to P2 by P1. So in this case, this is going to be 1. So V out of T then comes in this form, where in this situation you can write the Tn, that is the expression, that the time at which you want to produce your output. At which you want to produce your output, because both are going to be P1 now. So Tn that we are representing is the Tp1. That means the time constant corresponding to the pole P1. The time constant corresponding to the pole P1. So V out of T, then we can look at the frequency response of V out of T, or the time domain response, settling time of V out of T. And then we can assume, we can find out the tau graphically also. Once that tau is known, I can give it a stabilization time as 5 tau units. That will give me the response time. That will simply give me the response time. Okay. So very easily we can see that we can get an expression for when P1 and P2 are overlapping each other. Now it may be a case where M is not equal to 1. And again, if we solve this equation, the complexity is a little more. Take more time for us to analyze this equation, and then we come out with an expression which is given by this, where M is P2 by P1. Remember. This I have directly taken, I have not solved it. Maybe you can solve the equation. Okay, where P2 is not equal to P1. The two poles are not equal to each other. Or we can also solve for a case where P2 is much greater than P1. Then your V out of T will be mostly controlled by the first pole P1. So we can all go for three cases, find an expression for. So in this case, if I assume P2 to be much greater than P1, then my tau P will match with the one that we are getting for single stage comparator. It will match, expression will match for that. Remember that. Okay, here expression will have an impact of both P1 and P2, that is the pole P1 and the pole, so tau corresponding to P1 and the tau corresponding to P2. So this is what you get T after solving all these expressions, use the mathematical series, neglecting higher order terms, you get the Tp corresponding to two pole system as VOH plus VOL by M AV0 into Vin. This is what is given. You can also cross check with your own analysis. So The expression for the propagation delay for a two-pole system. This is for a two-pole system. Now this is when two-pole system is operating in a, or my op-amp, two-stage op-amp is operating in a linear mode. Suppose it is operating in a slew mode. If it is operating in a slew mode, what will happen? I have to now look at the slew rate of each stage. So now just before that I start with slewing response, what does this graph indicates? This shows you the settling time with respect to M, where M is different values. So M is equal to 1 when both poles are overlapping, and M is other than 1, that is less than 1 or more than 1. So what does this pattern suggest? That as P2 is much greater than P1, that means the settling time is less. It is improving. It is taking less time to settle down. It is taking less time to settle down. Okay? So two-pole system is more the poles in the system, dominant poles, sluggish will be the response. Very easily we can say because your 3 dB will be less. Correspondingly, because your 3 dB is the effect of two poles taken together. It is because of a combined system that 3 dB frequency is coming from the impact coming from all the poles in the system. And we know that is usually less than the lowest pole. It is less than the lowest pole. Okay, as a result, the response becomes more and more sluggish, or time period becomes more and more large. Fine, so we move on to the slew response. So if my output is slewing, that means in a two-pole system, which one has a high chance of slewing? Which stage has a high chance of slewing? Normally second stage, because first stage will produce a large output, suppose. As a result, the second stage will have a large input at its input terminal, large signal. As a result, you may have a second stage going into the slewing mode. So how does the slew happen in this case? So if there is a large signal here, so that means this node voltage will go very high. So this VGS will be less, M6 may go to cutoff. M6 may go to cutoff. So in this situation, as we say, one of the transistors goes to cutoff. Then it is only the discharge happening. So only I7, M7 is conducting. So your V out is discharging through M7. In a normal situation, what is our slewing current through CL? It would be the difference of M6 and M7. It would be the difference of M6 and M7 because both are conducting. Clear? So either for discharging it would be M6 minus M7, or for discharging it would be M7 minus M6. In a linear condition, in linear operation, where both the transistors are conducting. When one goes to cutoff, suppose it is very high, this goes to cutoff. Then the total discharge will happen through I7. The total discharge will happen through I7, and if this node voltage goes very low, then this conducts more than the I7 current. This will conduct a very large current, more than I7. In this situation, the charging will happen, it would be I6 minus I7. Then it would be done with respect to I6 minus I7. And if I6 is much larger than I7, it's roughly equal to I6 by CL. The slew rate would be roughly equal to I6 by CL. In case I6 becomes so much that I7 is negligible in comparison to that, in that situation only. So if we look at the slewing response of the output stage only, so first of all, in a slew mode, the total power consumption is because of the delay coming from every stage. Is because of the delay in a two-stage linear mode operation. It is actually a combined impact. We do not compute the delay of every stage and add. That we don't do. But in a slewing response, we actually do this. We find out the delay for every stage and then add all the delays together. That gives you the total propagation delay. That's the total comparison time the all complete structure will take. In a normal situation, we don't do that. We find out the TP expression in terms of poles P1 and P2 by using the charging and discharging equations of V out with respect to V in time domain. This we don't do in slew rate. We simply take every stage. Depending on slew rate, we find its T slew or T and then add all the T's together. Simply add all the T's together. Okay. So slew rate can be discharged or it can be charged. So we may have slew rate minus. We may have positive slew rate or a negative slew rate. So positive slew rate, as I said, it is because it is charging. This node is charging, it will charge through the current. So when this node voltage is going low, it will have a very heavy VGS. I6 will be very high. So net current going through CL will be I6 minus I7. So I6 minus I7. Charging, output is charging. It's going high, so positive slew rate. Output is going high, positive slew rate. I6 minus I7 by CL. For negative slew rate, when output is discharging, it would be only, here I assume that I6 goes to cut off, then I have only I7 by, clear? So now you can write the expression for I6 and I7 where we assume that both are operating in a saturation state and accordingly you find out. Replace every expression with its saturation region expression. So mu and Cox W by L, VGS minus VT, okay? Everything you will write and then we find out the correct value for the slew rate. So with this slew rate, we obtain the expression for T. How do you find T? Slew rate will be, the T will be, T slew will be CL into, yes, what will be T slew? Slew rate is change in voltage by change in time, output voltage. And that is nothing but I6 or I by CL. I by CL, so slew rate is known to you, multiply it by, sorry, if slew rate is known to you, that is dV by dt, differential of voltage with respect to T. So if voltage swing is known to you, you can find out T. You can find out T. You can easily find out the T value. The time taken by the circuit to have a full swing, output node to have a complete swing, whichever swing you are taking. For minima to maxima or maxima to minima. Fine, so now we say that which point we should take as a trip point. Trip point means the input, that value of the input at which output will change its state. Something similar to inversion potential or switching threshold. Remember in inverter, we have something called as switching threshold and this output stage itself is like an inverter. This is nothing but an inverter only. Here we are treating it like an amplifier, but in digital it is working like a inverter. So when we say that when input is going high, output is going low, there is a specific point of input at which we say that output will change its state. We call that voltage as a switching threshold. Here we call it as a trip point. Trip, what is that input at which the output will trip? Okay, so again we assume that in this situation, whereas in digital, we do not guarantee that both of them are in. How do you find the switching threshold? We assume that both the load and driver, they are in saturated because this is a point where we assume that V out is equal to V. We define our switching threshold at a point where V in is equal to V out. So at this, both transistors, upper and lower, they are in saturation state. So we equate the two currents. Remember, this is how we find out expression for V switching threshold. That's what the same method we will employ over here. So we find M6 and M7 to be saturated and then we find out an expression for I6 and expression for I7 and then we equate them together. We equate them together. The same method as we use in digital. And when we equate them together, then the input at which expression for V in will give you the expression for the switching threshold or trip point. Okay? This is where I will say my input will trip. That is, for a certain V in where M6 and M7 both are saturated and they have the same current, okay, I find out an expression. So suddenly this V out will take a swing from 0 to VDD or VDD to 0. In your saturated case, it may not be full swing, it may be VDD minus V overdrive, or minima can be V overdrive. If you are assuming both transistors to be in saturation. Okay? So this gives you the expression for the trip point. We get an expression for the trip point, that is nothing but the switching threshold. So we only need to know that if this is my input at the input terminal, my output will switch. Okay, accordingly I can find my T, because I have to find out the T corresponding to V in trip. V in trip. So when V in becomes V in trip, T becomes my T series. T becomes my T series. Okay? So only that delay that has to be calculated. We have to calculate our delay till V in reaches its V trip point. So this is about a two-stage comparator. We have another topology. This is known as a two-stage push-pull. What's the difference in this one and the previous one? What's the difference between this and the previous topology? What's the previous topology? Look here. That was also two-stage op-amp. Here, your load is a current source load. Clear? In the second structure that I am showing you, look here. This is not coming from here. Rather, there is something in between. What is this? What is this? What is from where you are causing? You are taking this signal. Why I have included M8 and M9? What is the reason for including M8 and M9? Remember M1, M2, diode connected M3 and a diode connected M4. So this is a fully differential amplifier. Be very careful. This node and this node, they both are two output nodes of a fully differential amplifier composed of M1, M2, M3, M4. Okay? So this is one output node. This is another output node. So one output node is fed. This is a common, what is this? Common source amplifier with a diode connected load. M8 is a common source amplifier with a diode connected load. What will be the gain of this stage? GM8 by GM9. I can make two GMs to be same by choosing same overdrive. I can make two GMs to be same. So gain of this CSA will be 1. As a result, whatever is this output, it will directly come at this node. As if I am providing the signal from here to here. The signal is transferred as it is without any problem, without any change. The signal is getting transferred from this node through M8, M9 to this node. And the second output is directly going to M6. So one transistor is fed by one output node, other transistor is fed by other transistor node. That means signal goes to both. One has a V out positive, other is getting V out negative. That means both these transistors are getting the signal. Input goes to both. There is a signal present at the input of both transistors. So this amplifier till date, whatever CSA we have seen, input goes to only one transistor, other is a current source load, diode connected load, resistive load, no? But here input is going to both and it is working, it's nothing but a similar to a CMOS gate. Let me show you now if you are still not getting Let me draw it on the sheet of paper so that you understand in front of you. This is a CMOS inverter. What is this? What I am doing over here? Huh? Input goes to both. Input goes to both. Now for me, this is a push-pull amplifier. This is a push-pull amplifier. The trouble here is the DC at this point is same for this, same for this. DC, so I can only have a DC of this is 1 volt and this is 0. So I can have a DC of, so do 2 volt, I can have a DC of 1. So that VGS is same for both. But then this will give you 1 volt VGS here, 1 volt VGS here. If I make it 0.7 volts VGS here, so this is 0.7, this will become 1.3. So that means if I optimize on VGS of one transistor, for other it becomes excessively large. So I cannot optimize for both. So I break from here. I redo it. So this is my Vin. Vin is given to 1, 2 directly. One transient is given directly. Another is given to a common source amplifier with a diode connected load. So this output has a gain of 1. So GM8 by GM9 taken as 1, same. So Vin comes here, gain is 1, so this gain now is given to this. I can choose this value. I can choose a DC at this value. This can be chosen. This is 2 volts. I can have 0.7. This I can set at 1.3. This can have a DC of 1.3. But then I can choose a DC here independently. I can choose this to be 0.7. It's up to me. So now this will have a DC of 0.7 and this will have a DC of 0.7. Both are given independent DC bias, but they are getting the same AC signal. So it is the same circuitry drawn in a different way here by inclusion of this circuit. This is what we are doing in our slide. Okay? So now I am giving AC signal to both, but I am optimizing the DC for both independent of each other. That's what we are doing. So look at the slide. This is what is your intermediate stage. This is a push-pull amplifier. It is again a CSA. But then what is the gain of this push-pull? Normal situation. What is the gain of a CSA? Normally, GM RO6 parallel RO7. No? If I am not giving if this is my situation. If I am giving this kind of a, this is V bias, this is V in, this is V out. M6, M7. Gain would be given by this. What is the gain here? What is the gain for this? This is a gain for this structure. What is the gain here? Input goes to both. Here input goes to only M6. In this situation it would be GM6 plus GM7 RO6 parallel RO6 with a negative sign. So push-pull amplifier has nearly twice the gain. Push-pull amplifier has nearly twice the gain. So in your two-stage amplifier, I am increasing the gain of the second stage by making it a push-pull topology. By making it a push-pull topology. Clear? I am increasing the gain. Remember, increasing the gain means you are improving the resolution. You are improving the resolution. resolution of a comparator. And push-pull will also help you in achieving high slew rates. Push-pull output will help you in high slew rate. That is also possible. You may get a very high slew rate here. A cascode, that can also be a cascode with push-pull. That can also be a comparator. I am saying we are not doing anything. It is simply simple op-amps which are working as a comparator. Simple op-amps which are working as a comparator. This folded cascode with push-pull will give you a very high gain. This will give you a very high gain. All are two stages. If your capacitive output is very large, here, if this output is very, very large, very high loading is there. Suppose in some cases comparator is driving a very heavy load. Then I cannot work with this. Why? Because it will slow down. A very large capacitive load means time constant will be tremendous. So here we make use of logical effort. For driving a very heavy load, what do? We drive it through a chain of inverters. That's what I am going to do here. After my comparator, I put a chain of inverters. Look here, this is what I am doing. This is my comparator, two-stage comparator. And then I am putting a chain of inverters which may be scaled. Scaled buffers. The W's would be increasing in a certain proportion. Everybody has done logical effort? Goa campus?
Yes, ma'am.
So you can have a chain of inverters. M8, M9 is one buffer. M10, M11 is another buffer. You can have n number of chains, n number of inverters. Then how many inverters you should have, that you decide. You can find out an optimum value for n. Because we want T to be minimum. So here I am mixing. Now it is a mixed signal design. A very crude example of mixed signal design where you have analog and digital circuits mixed up. Okay. So again it is an n stage. I will call it as an n stage comparator now. I will call it as an n stage comparator where or which is suitable for driving a very heavy capacitive load. Driving a very heavy capacitive load. Okay? So the capacitive load here becomes less because it is only the capacitive load coming from M8 and M9. So time constant for this comparator becomes less. Okay, so tau for this stage will become small. This is a different self-biased differential pair. This I will not discuss. Maybe you can look at it on your own. This topology is also given in Allen and Holberg's book. Okay. Folded cascode comparator. I think this is what I have. Now we come to multi-stage. Multi-stage means many differential pairs are put one after the another. Many amplifiers. N stage. I have discussed only two stages. So when you put too many amplifiers, n number of amplifiers, so multi-stage implementation. Now from one stage, two stage, we are slowly moving towards n stage comparator, multi-stage comparator. It is all analog. It is all analog. So for multi-stage comparator, if I want to find out the tau, I have to take the whole cascade as a single unit. I have to treat the whole cascade of n stages as a single unit and find out the tau for those n stages together. Remember, whenever you have n such amplifiers in series, the frequency response of all of them when you draw it on a single axis, okay, they all affect each other, and when you draw the equivalent, you will have an omega naught, which may be because of omega naughts of all n stages. that is decided by the omega naughts of each stage. Similarly, zeros will also be because of the zeros of each stage. Poles will be because of the pole frequencies of each stage. Okay, so how to find that omega naught for n stage? If I say I am putting a differential pair as a comparator and it is n stage amplifier, then suppose for simplicity I am just repeating that amplifier once again or for n stages. I am not doing anything else. Simple that n amplifier, which is my differential pair, a simple differential pair, I am repeating it n times in a cascade. So every amplifier will have the same frequency response because they are identical stages. Because I am repeating the same stage for n stages. Suppose every stage has a single pole response, it has only one pole. It has only one dominant pole. So all n stages will also have one dominant pole each. Each will have because of the same transfer function. So if I say that there are n stages in a cascade which are open loop stages all, and this has a transfer function given by this expression. As is equal to A naught 1 plus S by omega P, where omega P is a dominant pole for this stage. This will also have the same transfer function. This will also have the same transfer function. So in this situation, the transfer function for all stages taken together, let me call it as AVS. The transfer function, so V out of this upon V in of this will be the transfer function for the n series cascade. So that will be the multiplication of transfer function of n stages taken together. Multiplication of n stages taken together, that means this factor to be multiplied with the same function n times. So this A naught will become A naught to the power n, and 1 plus S upon omega P will also have a power n. This will be the transfer function for this n series cascade. So what I am doing here is that I am not going for a very high gain amplifier. Remember, we say to have a good resolution I should have a very high gain, which I try to implement in one stage or two stages. Now I am saying, okay, let me not have one or two, let me have n stages. In that situation I will have n stages, but the gain per stage will be less. I need not design every stage with a very high gain. But because there would be n series cascade, the total gain will become very large. So that would certainly give me a very good resolution. Okay, as a result, now I am saying that I have now lots of stages put together in series with low gain. With low gain. So if this is my implementation, what would be my tau of propagation delay expression, of propagation delay model? So I start with this expression. This is my transfer function for n stage cascade. So I start with this and do little bit of analysis. So this is my transfer function for the n series cascade. Okay. Now I am saying that if your expression for n series, I can also write for n series cascade, let me say the total transfer function AV of S. AV of S is equal to some A naught n, which is the DC gain of n series cascade, divide by 1 plus S upon omega naught n. What is omega naught n? It is the 3 dB frequency, overall net 3 dB frequency of n series cascade, where this each omega naught n will be composed of omega naught for first stage, omega naught for series second stage, omega naught for third stage. It will have some combination of all of them together. It would be some combination. Now, if I take the magnitude of this function, this would be magnitude of A naught n. So this is magnitude I am finding at omega equal to omega naught for n series. So this expression will come out to be A naught n magnitude divide by root 2. Divide by root 2. Now actually my AVS, I naught is given as A naught to the power n, where A naught is the DC gain of every stage, each stage. Divide by 1 plus omega by omega naught, S by omega naught to the power n. This is to the power n. So that means that if I take the magnitude of this function, the magnitude of this would be A naught to the power n, and magnitude of this should be equal to root 2. Magnitude of denominator must be equal to root 2. That's what I am writing in my slide. That's what I am writing. At omega equal to omega naught n, magnitude of this function will be A naught n by root 2. That means magnitude of this function must be root 2. Okay? So if you solve this, I get the expression for omega naught n in terms of omega naught of every stage. Omega naught of every stage. So this is omega naught for n series cascade will be omega naught root of 2 to the power 1 by n minus 1. So I have got the 3 dB frequency for n series cascade. 3 dB frequency for n series cascade. Naturally my tau will be inverse of that. My tau will be inverse of it. Okay, so if I have got omega naught, I can find this expression. Suppose you are given omega unity. So I can express omega naught n in terms of omega unity also, or UGB also. Unity gain bandwidth. How will you rewrite it? Because omega naught will be omega unity divided by gain of every stage. Remember, for a single pole transfer function, UGB is equal to gain times 3 dB. So I am using that expression. So here I am replacing omega naught by omega unity or UGB, which I get through this equation. So omega unity is gain times omega naught. So gain for each stage is A naught, which is nothing but total gain to the power 1 by n. Total gain to the power, because there are n stages, nth root. Nth root you have to take. Total gain for n series cascade, nth root for that. And I simply substitute. So this is giving me, this is omega naught n. Now I can replace it as UGB of n series cascade. UGB of n series cascade given by this expression. So now whether you are given a 3 dB or you are not given a 3 dB, you are given UGB of n series cascade. You can work. So I can show you a small example. So this is all that small derivation that you can just look into. And then a small example. First of all, let us see the example. Look here. If I am taking 3 stages. Look at the example. I am taking 3 stages, and every stage has a gain of, sorry. What I am doing is, I am designing a 3-stage amplifier for which I require a F naught or omega naught n, for which I want a omega naught for 3-stage series. I desire a omega naught of 3-stage series. So from omega naught of 3-stage, I will take the inverse. Will give me tau for 3-stage series. Understand? So omega naught for 3-stage series. Okay, I use this expression. I have to use this expression. But you are given a unity gain bandwidth. You are given every stage gain is 10,000. No, A total is given. So A naught to the power n is given. A total is given. So this would be A naught will be this 10,000 to the power 1 by 3. 1 by 3 because it is a three stage amplifier. So if I substitute everything in this expression, we get omega naught n. I am getting f naught n because you would be then dividing by 2 pi. Okay. This comes out to be 24 megahertz. For 24 megahertz corresponding tau comes out to be 7 nanoseconds. So if I give it a stabilization time as 5 tau total, it comes out to be 35 nanoseconds. That is for 3-stage cascade with every stage having a gain of 10,000 to the power 1 by 3 and a UGB of 1 gigahertz, you are able to get total response time of 35 nanoseconds. Now, if we want to know whether how much n I should take, is it beneficial for me to choose n very high? Is it beneficial? So I try to plot. So I try to give for different values of n, I try to plot the step response with respect to time. That is the linear settling time I am plotting. Step response is linear settling time. Remember? When you give a step input, output is again a step. Output, we call this as a, from this we get our linear settling time. Through this response we get our linear settling time. So step response gives you linear settling time. So I am plotting the step response for different n's, for different n. 3 different colors are shown. N equal to 1, n equal to 3, n equal to 5. So what does it show? That in the same equation if you are using, but n you are varying from 1 to 5. So 1 gives you this plot, very sluggish response, you are getting very sluggish response. Okay. Then it is 3, it's better. The point where it is reaching its tolerance limit. Okay, output. This is the point. This point says that your output is say 95% of your maxima. We define a limit that my output reaches 50% of its maxima. I will say I have reached my output. Or 63% or 90%, this limit I define. So suppose my limit is shown by this bluish line or greenish blue line. Okay? So wherever it is reaching its desired voltage level, I assume this is my settling time. My input is applied at this instant. My step input is applied at this instant. For n equal to 1, n is reaching that voltage level at the output at this point. So this is your settling time. Maybe it's approximately 10 units. For n equal to 3, that is a green line. It reaches somewhere here. For n equal to 5, that is red line. It reaches somewhere here. So what does it show you? It shows that choosing a very large n is not suitable. We should optimize on number of n's. So here, if you want to have a faster propagation time, n equal to 3 is the best choice. N equal to 3 is the best choice. So this is something same as we get in logical effort. Remember, choosing too many stages causes your delay to increase. Choosing too less stages also causes your delay to increase. So we have a minima somewhere in between. We have a minima somewhere in between. Okay? So this is a step response that I have tried to get an expression for. The step response that we have plotted here. So this is the expression for the step response. V out when your input is a step. Expression for V out of t when your input is a step input. Very little bit of complicated equations that is getting. Okay, now we move okay, optimum number of stages. How many optimum number of stages you should have? What are the optimum number of n stages you should have. So again, you can write the expression for your V out of t, get its t, and then t has to be minimized with respect to n. T, that means propagation delay time, has to be minimized with respect to n. Something which people, they are getting that if you're choosing a gain of less than 1000, it is given by n optimum is given by this expression. That means if each stage has a gain less than 1000, then this above limit is true. That n optimum lies somewhere in between, given by this equation. A curve fitting, a line has been tried to fit, and then we are getting a straight line approximation. For gain for each stage less than 1000. Find delay versus, I think this is the same thing we were getting in our logical effort also. So if your n is increasing, delay does not change much, rather it starts increasing. So increasing here, so minima somewhere here, this point. That's what we were getting in logical effort also. So now we move on to the next. That is, how do we have seen how to improve the resolution. That is, increase the gain. Either by using a single stage or two stage with very high gain, or use multiple stages to achieve high gain. But then, this time we are focusing on the delay minimization and improving the resolution. As a comparator, two things we are looking at, how to improve the resolution and how to decrease the delay. Now we come to the third parameter, offset. Because offset can affect your resolution once again. Offset can also cause the resolution to degrade. I want it to be a very good resolution. What is the resolution? Minimum voltage difference that can be sensed by the comparator. I want it to be as low as possible. But if offset is there, it can cause V in to be large, minimum V in to be large. How can I address the problem of offset? Because offset will be there. Systematic offset you may remove, but random offset you cannot remove. It is because of process variations, mismatches. I cannot remove. So if offset has to be removed, it cannot be removed just like that, removing it by doing something. You have to find out a design technique to negate its effect. Some method, because it will exist, but then you have to cancel it out. When you get your output, it has to be cancelled out. So that technique is called as auto-zeroing. Auto-zeroing technique, where offset, at the output offset comes, but then we generate a term minus V offset, so that the net V offset gets cancelled. Output comes as a pure term without any impact of offset voltage. That is what we mean by auto-zeroing. So this we shall do next week. Okay, just be ready with your projects, project reports. Anytime I can ask you to submit, and then we can have a evaluation the next day. Anytime, just be ready with that.